Welcome back. In the last video, we derived the projection formula. In this video, we're going to take a look at how to use that in an example. Here, the example is to find the orthogonal projection of a vector u onto a vector v, where the vector u is given by 4, 1, and the vector v is given by 3, 4. Let's recall the interpretation of this orthogonal projection. Remember that the direction of v we can think about as the line that extends off into either direction. That's called the direction of v. And we're going to come back to this point over and over and over again. It's the set of all scalar multiples times v, where this is a scalar vector multiplication for any scalar. It's literally running through the entire set of possibilities in scalars, right? So to be on the line defined by the direction v, you just have to be some scalar times v. The entire line is the set of all scalar multiples of v. Okay, so that's that dotted line. The idea of finding the orthogonal projection is to literally force the part of u that we're interested in to be along that line so that this angle is at 90 degrees, and then we call this vector, the one that leads up right to the edge of that little dotted line there, this is the vector p. That's the one we're looking for. What's really cool about this is if we do that vector well, we can simultaneously construct the orthogonal vector r, which is the one that comes directly out this way. I won't draw that for now because that's not what we're asked to do in this problem. Okay, so we want to search for p. Let's recall from our previous video that if we want p to be the projection of the vector u onto the vector v, we're going to do this by taking the vector that we want, dotted with the direction that's defined, and then we take that over the 2 norm of our direction. And this was called the scalar projection of u onto v. And another way to think about this is it's the amount of the unit vector in the direction of v that you need to travel to get directly orthogonal under u. And then remember, this is going to be a vector. This whole thing is a scalar because u dot v is a scalar, the 2 norm of v is a scalar, division is a scalar. So I actually need a vector here, and the vector was going to be this one. Okay. Let's go ahead and do a quick side note. I'm going to need to calculate these. So I might as well do that here. Let's find the 2 norm of v. And remember that v was the vector 3, 4. I'm feeling a little bit sick of square roots right now, so I'm going to do the 2 norm as v dot v, and I'll take the square of it. So this would be 3 squared, which is 9, 4 squared, which is 16. Of course, that means that the 2 norm squared is 25, and the moment that I know that, I can, at the very, very end, I can take the square root of this, and I get that the 2 norm of v is 5. And we can do another side note quickly to recognize that u dot v, as a quick recall, u was 4, 1. We just said that v was 3, 4. So this is now 12 plus 4, which is 16. If we go back up here, we can now use our side calculations to substitute in. This is going to be 16 divided by 5 times 3 comma 4 divided by 5. And I think I'm going to hammer home a point that I said verbally but I didn't show. When we write a vector divided by a scalar, what we really mean is please take the scalar 1 over the denominator and multiply it by the vector. So this operation here is scalar vector multiplication. So now I've got 16 over 5. And then I don't know what you want to do first. Do you want to bring this in or multiply it out? I kind of want to leave this out in front. So now I have my projection. So this is P. What's really interesting about this is if I think about the scalar projection, the scalar projection of U onto V was 16 over 5. And that is actually the length of this vector. Here it is right there. And I'm going to go ahead and confirm that for you. I'm going to claim right now, without it, we showed this in the last video. And I'm actually going to show that this is true by looking at this one. So here, if you take the 2 norm would be the, let's see, the square root of 16 over 5 times 3 over 5 squared plus 16 over 5 times 4 over 5 squared. Notice I can pull out a 16 over 5 squared because it's in both forms. And then I'm left with 9 over 25 plus 16 over 25. Okay. Yeah, I actually am going to break this up into 2 right there just to make it easy on myself. So now this is 16 over 5 squared. And then do you notice that this is now 25 over 25? Of course it is. We said that that was a unit vector. That was the length of the unit vector. Square root of this thing squared is just the absolute value of it, which is 16 over 5. And indeed, we've just confirmed algebraically what we confirmed analytically in the last video, which is the length of P is actually the value of the scalar projection of U onto V. That shows you how to use this. We're going to use this pretty extensively when we start talking about distances between points and planes, distances between points and lines, distances between points and surfaces. And this gets into an opportunity to do optimization, which you'll see later in this class. All right, we are now ready to move on to lesson 4. Yay!